The best way to show how to use impedance in circuit analysis is by working examples. So I'll spend most of this video solving problems. Notice that I'm using exactly the same analysis approaches we used earlier in the course for purely resistive circuits. First, let's review impedances. Impedances are a way to represent a circuit element's voltage-current relationship in the frequency domain. Impedance, which is usually represented by an uppercase Z, is the ratio of the voltage phasor between a circuit element's terminals to the current phasor going through the circuit element. When we define the voltage and current phasors, we still need to use the passive sign convention. The assumed positive current phasor enters the assumed positive voltage terminal. The impedance of a resistor is just its resistance. For an inductor, the impedance is J times the frequency in radians per second times the inductance, or J omega L. For a capacitor, the impedance is 1 over J times omega times C. This is equal to the negative of J divided by omega times C. Steady-state sinusoidal circuit analysis can be made really easy by using impedances to represent the circuit elements. Before we discuss circuit analysis, though, I want to introduce a little bit more vocabulary relative to impedances. Impedance is, in general, a complex number. In rectangular coordinates, impedance has a real part, usually denoted by R, and an imaginary part, usually denoted by X. R, the real part of the impedance, is called the resistance. The imaginary part of the impedance, X, is called the reactance. Although phasors and impedances are both complex numbers, impedance is not a phasor. Impedance defines the relationship between voltage and current phasors, but impedance itself doesn't provide the magnitude and phase angle of a sinusoid. Remember, all phasors are complex numbers, but not all complex numbers are phasors. I won't use admittance in this class, but I do want to introduce the term. Admittance is just the inverse of impedance, and it's usually represented by a capital Y. Admittance is also typically a complex number. In rectangular form, it's written as a real part G plus an imaginary part B. G is called the conductance, and B is the susceptance. Impedance is super useful because if we represent the circuit elements as impedances, we can now do steady-state sinusoidal analysis exactly the way we analyze purely resistive circuits. That means that the tools like circuit reduction are now appropriate. We couldn't combine resistors, capacitors, and inductors into a single equivalent element in the time domain, but we can combine different types of elements in the frequency domain if we represent them by their impedance. Likewise, we can use voltage and current dividers, nodal and mesh analysis, and Thevenin's and Norton's theorems almost exactly as we did with purely resistive networks. In order to take advantage of these tools, we represent the signals in the circuit, the voltages and the currents, as phasors. We also represent the circuit elements, resistors, capacitors, and inductors, by their impedances. Then we just proceed with our analysis the same way we would if the impedances were resistors and the voltages and currents were constants in the time domain. The only penalty is that we have to do a little complex arithmetic. I'll spend the rest of this video doing examples to demonstrate how this works. My first example is this circuit. I have a voltage source that's in series with a resistor and an inductor. The applied voltage is sinusoidal, and I'm looking for the current out of the source as time goes to infinity. So this is a steady-state sinusoidal problem. If I convert this circuit to the frequency domain, I can combine these elements into a single equivalent impedance and then use Ohm's law to find the current based on this voltage. So first we need to determine the impedances for these individual elements. For a resistor, the impedance is just the resistance, so that's 200 ohms. For an inductor, the impedance is J times omega times L. That's J times the frequency is 100 radians per second, times L, which is 2 henries. So this is J 200 ohms. And the frequency domain circuit becomes this. These are the impedances of these elements. I've converted the voltage source to phasor form, 5 at an angle of 15 degrees, and the unknown current is now a phasor I underscore. I can now combine these two impedances in series to get an equivalent impedance of 200 plus J 200 ohms. Then this current is this voltage divided by this impedance. So I is 5 at an angle of 15 degrees over 200 plus J 200 ohms. Division is easier in polar form. So this is 5 at an angle of 15 degrees. Converting this to polar form, the magnitude is the square root of the real part squared, 200 squared, plus the imaginary part squared, which is 200 squared. And the phase angle is the inverse tangent of the imaginary part, 200, over the real part, which is also 200. So this becomes 5 at an angle of 15 degrees. The magnitude is 200 times the square root of 2. And this angle is 45 degrees. So I, as a phasor, the magnitude is 5 over 200 times the square root of 2. The phase angle is 15 degrees minus 45 degrees. Take the angle of the numerator, subtract the angle of the denominator from that, which becomes minus 30 degrees. So the current as a function of time, as time goes to infinity, is this amplitude, 5 over 200 times the square root of 2, cosine of this frequency, 100 radians per second times time, plus this phase angle, which is minus 30 degrees. And there's my solution. My second example is based on this circuit. My applied voltage is a sinusoid. It has an amplitude of 5, a frequency of 3 radians per second, and a phase angle of 0 degrees. I'm looking for the current through this capacitor as time goes to infinity. This is a frequency domain problem. So the first thing I'm going to do is find the impedances for all of these circuit elements. The impedances of resistors are just their resistances, so I don't really need to calculate anything for those. The impedance of a capacitor is negative J over omega C. That's negative J over the frequency is 3 radians per second, and the capacitance is 1 over 9 farads. This turns out to be negative J3 ohms. The impedance of an inductor is J times omega times L, which is J times the frequency is still 3 radians per second, times the inductance, which is 1 Henry, which turns out to be positive J3 ohms. Now, if we convert this circuit to the frequency domain, the applied voltage is a phasor. It's 5 at an angle of 0 degrees, and the current is represented as a phasor. The circuit elements are represented by their impedances. Now let's plan how to approach this problem before we actually do anything. With nodal analysis and mesh analysis, those will both end up with 2 equations and 2 unknowns. That's not always a problem, but it could be that we have an easier way to do this. Let's take a look at circuit reduction techniques. If I know the current out of this source, say I sub S underscore, these 2 elements are in parallel with this capacitor. So if I know this current, I can use a current divider to find I underscore. So approach 1. I'll find IS and use a current divider. Another option would be to find the voltage across here, call that V1 as a phasor. So if I combine all of these into one equivalent impedance, say ZEQ1, I can use a voltage divider to find V1. Now if I know this voltage, this current is just this voltage over negative J3 ohms. These both look like about the same amount of work. I'm going to sort of arbitrarily choose to use approach 1. To use a current divider to find I, first I need to determine the current out of the source. I can do that by determining the equivalent impedance, ZEQ, of this entire network, dividing this voltage by that impedance, which will give me this current. So to determine the equivalent impedance, these two elements are in series. Their equivalent impedance is 3 plus J3 ohms. Now this impedance and the capacitor's impedance are in parallel. If I call that combination ZEQ1, I can calculate the equivalent impedance by taking the product of the two impedances divided by the sum of the two impedances. It's the same formula as for parallel resistances. So that becomes 3 plus J3 ohms times a negative J3 ohms divided by 3 plus J3 ohms plus a negative J3 ohms. This and this cancel. This 3 cancels with that 3. So this becomes minus J times 3, which is minus J3. Negative J times J is positive 1, so that becomes a 3. Now ZEQ, this entire impedance is in series with this 1 ohm resistor, so that's 1 ohm plus ZEQ1, which is minus J3 plus 3 ohms. This is 1 plus 3, which is 4, minus J3 ohms. Now let's use that impedance to find the current into this network. This is my equivalent circuit that I can use to find the source current I sub S. The equivalent impedance was 4 minus J3 ohms. So this current, according to Ohm's law, is going to be this voltage divided by this impedance. So I underscore S is 5 at an angle of 0 degrees over 4 minus J3 ohms. Division is most easily done in polar coordinates, so I'll convert the denominator to polar coordinates. This is 5 at an angle of 0 degrees. The magnitude is the square root of 4 squared, the square root of the real part squared plus the imaginary part squared. The imaginary part is negative 3. And the phase angle is the inverse tangent of the imaginary part, minus 3 over 4. So this is 5 at an angle of 0 degrees. 16 plus 9 is 25. Square root of 25 is 5. So this is 5 at an angle of, this turns out to be minus 36.9 degrees. So amplitude-wise, the 5's cancel. This has an amplitude of 1 and a phase angle of 0 minus a negative 36.9 degrees, which is positive 36.9 degrees. Now let's use this source current in a current divider formula to find the capacitor current that we originally wanted. This is our current divider schematic. We know that the source current is 1 at an angle of 36.9 degrees amps. We have a parallel combination of impedances and we want the current in through one of those impedances. This is the perfect case for a current divider. So I, the phasor, is equal to the total current, 1 at an angle of 36.9 degrees, times the other impedance, 3 plus J3 ohms, over the sum of these two impedances, 3 plus J3 minus J3 ohms. The formula is the same as the one you'd use for resistors. The current in one of the legs is the total current times the resistance in the other leg divided by the sum of the resistances in the two legs. This and this cancel. This 3 cancels with these two 3's. So I is equal to 1 at an angle of 36.9 degrees times 1 plus J. Multiplication is most easily done in polar coordinates. So this becomes 1 at an angle of 36.9 degrees Converting this to polar coordinates, the magnitude is the square root of the squares of the real part and the imaginary part. The real part is 1, and the imaginary part is also 1. The phase angle is the inverse tangent of the imaginary part, which is 1, over the real part, which is also 1. So this becomes 1 at an angle of 36.9 degrees times the square root of 2, and this is 45 degrees. When I multiply phasors in polar form, I multiply the magnitudes. 1 times the square root of 2 is the square root of 2, and I add the phase angles. 36.9 plus 45 is 81.9 degrees. That means that the current as a function of time, as t goes to infinity, has this magnitude, square root of 2. Cosine of the frequency is 3 radians per second from our original problem statement. 3t plus 81.9 degrees, and there is finally our solution. We now have a wide range of analysis approaches available for solving steady-state sinusoidal problems. So it's important to make sure you look closely at a problem and develop a strategy for solving it before you start. Keep all of your options open and make sure you use the one that you feel is the least amount of work. Nodal and mesh analysis in particular can be prone to math errors when complex arithmetic is involved. However, not all circuits can be analyzed using circuit reduction techniques, so I'll spend the rest of this video on nodal and mesh analysis. In this circuit, I want to find this current phasor, I sub c underscore, through the capacitor in this circuit, and I want to use nodal analysis to do that. In nodal analysis, I need a reference node. I'm going to arbitrarily choose that to be down here. That's my 0 volts. I really have only one independent node in that circuit. It's up here. So I'm going to label this node voltage V sub A underscore, since it's a phasor now. Now if I do KCL at the independent node, I have this current entering the node, which has to be equal to the sum of the currents leaving the node. This current is V sub A minus 0 over 50. And this current is V underscore A minus 0 over negative J80. If I clear this denominator, I get 10 at an angle of 20 degrees. 50 times 80 is 4,000. Times negative J, which has an angle of minus 90 degrees. That's equal to V underscore A times 50 minus J80 ohms. So V underscore A is equal to this, which is 40,000 at an angle of 20 minus 90 is negative 70 degrees, divided by 50 minus J80 ohms. So this is 40,000 at an angle of negative 70 degrees. The square root of 50 squared plus 80 squared is 93.34. And the arctan of negative 80 over 50 is negative 58 degrees. 40,000 over 93.34 is 424. And an angle of negative 70 minus a negative 58 degrees is minus 12 degrees. Now let's use this voltage to determine the current I sub C. Now we've got our node voltages. We can find this current the way we would do it for a resistive network. So this current, I underscore C, is this voltage, V underscore A, over negative J80 ohms. So this is 424 at an angle of minus 12 degrees over 80, and negative J has an angle of negative 90 degrees. 424 over 80 is 5.3, and negative 12 minus a minus 90 is plus 78 degrees. want to take another look at this example. In the previous approach, we were required to use nodal analysis, but I don't think that's the easiest way to do this problem. In this example, we know the current going into a parallel combination of impedances, and we want the current through one of the legs of this parallel combination. It's a perfect case for a current divider. So from a current divider formula, IC is the total current, 10 at an angle of 20 degrees, times the other impedance, which is 50 ohms, over the sum of the two impedances, which is 50 minus J 80 ohms. 50 times 10 is 500 at an angle of 20 degrees. Since 50 is a real number, it has an angle of 0 degrees. Over this, which is 94.34, we already calculated it at an angle of negative 58 degrees. So I underscore C is 500 over 94.34, which is about 5.3, at an angle of 20 minus a negative 58 degrees, which is positive 78 degrees. It's the same result we got earlier, we just got it more easily using a current divider. In this example, I want to use mesh analysis to find the voltage V in this circuit. This circuit has only one mesh loop. It'll be here, and I need to define that as a phasor I underscore 1. Now I'm going to create a constrained loop to account for the current through this current source. That's also a phasor. It's 10 at an angle of 0 degrees. Now I'm going to start down here and do KVL around that loop. Starting down here, I have 1 ohm times I1 minus 10 at an angle of 0 degrees plus J4 ohms times just I1 is the only mesh current going through that element, plus 2 ohms also times I1. Now if I group terms, 1 times 10 at an angle of 0 degrees is 10 at an angle of 0 degrees. I'll take that over to the other side. So 10 at an angle of 0 degrees is equal to I1 times 1 plus 2 is 3 plus J4 ohms. So I1, which is a phasor, is equal to 10 at an angle of 0 degrees over 3 plus J4 ohms, which is 10 at an angle of 0 degrees. This has a magnitude of the square root of 3 squared plus 4 squared, which is 5, at an angle that's the inverse tangent of 4/3, which is 53.1 degrees. So I1 as a phasor is 10 over 5, which is 2, at an angle of 0 minus 53.1. The voltage phasor that we're looking for is I1 times 2 ohms. 2 times 2 is 4 at an angle of minus 53.1 degrees.